Hello, thank you for joining us. This presentation will be probably about supply chains, asymmetric keys, and hardware. And we have a guy from Intel, John Barry. Hello, John. How are you?
Hi, everybody.
Perfect. And we are late, so the mic and the stage is yours.
Okay, thank you very much, Jakob. And thanks everyone for taking the time to join us here for this discussion today. As Jakob mentioned, there's this is all about the attestation of hardware devices and firmware, within the context of a digital system and the role of asymmetric key generation within that process. My name is John Barry. I work as a security architect with the Intel Networking and Edge Group, and together with my colleagues Marek Zmuda, Christine Severance-Williams, and a host of other colleagues, both inside Intel and in other kind of collaborative organizations, within the ecosystem. We've been looking at this issue, and one of the things that has emerged is a kind of a gap in the certification process that needs to be addressed in the context of that supply chain security requirements. So the purpose of this discussion is to introduce you to the gap, introduce you to a proposal that we have to kind of address that issue, and hopefully increase awareness of the need to have this process kind of fully certified and trustworthy for the benefit of all the stakeholders across the system. So just before we start, there's the usual legal disclaimers. I won't read all of these, but just suffice to say that the focus of today's discussion is very much on the kind of the protocols and the standards, rather than on any particular device or any particular implementation. So what are we going to talk about? So we'll start off by looking at the attestation process. Why do we do it? What does it mean? What does it mean for our customers? What does it mean for the ecosystem? We'll take a look at the protocols and standards that apply in this space. And in particular, we'll kind of focus on the use of asymmetric keys within that standard and protocol framework. Then we look at the process, how that asymmetric cryptographic implementation gets certified, and where the gap has emerged within that certification process. And finally, we'll wrap up with a look at the potential solution that we've been looking at in this area, and the kind of the status that is at within the kind of the standards development process. So, and I'll try and make this as interactive as possible. I'll leave, kind of time for questions and answers at the end. So, please submit your questions to Jakob, and hopefully we'll have lots of time for an interesting discussion at the end of the presentation. So what is attestation? So the purpose of attestation is really to give consumers and end users confidence in the provenance of the, both the silicon and the low-level firmware that runs on that silicon, that the supply chain hasn't been compromised in any way, and that the parts and the content that's running on those parts are genuine parts and match some defined quality criteria or some defined trustworthiness criteria. And the way that system works is, it starts off by authenticating the device itself. So, you start at the base layer with the raw hardware. And in that, hardware can provide measurements, both, associated with the configuration of the hardware or, associated with some kind of firmware or some code that's running on the device. And, this whole process, relies on, some kind of an external verifier, who uses a defined appraisal policy and the evidence that's presented by the device and compares that to some kind of a reference manifest to determine the authenticity and the provenance of the device and the all the associated collateral that goes with it. So that's essentially what we're trying to do. We're trying to build confidence within the ecosystem so that if you've got everything from a huge data center to a rack within a kind of a small business, that you can be assured that your workloads are running on kind of genuine parts that have not been tampered with, and that your, the kind of the supply chain that's associated with your infrastructure has not been compromised. And obviously, supply chain security has been, very much a hot topic across the industry for the past number of years. And a lot of kind of different standards and interlocking kind of standards and protocols have emerged in this space. I've listed a few of them here. This is by no means an exhaustive list. There's, I've only, kind of scratched the surface here, but there's, two in particular that I want to focus in on for the purposes of this discussion. One is the device identifier composition engine. This is commonly abbreviated to DICE from the Trusted Computing Group. And the purpose of this is to generate an identity for a particular device and the kind of the first layer of mutable code that runs on that device. And the way that is done is, you start off by taking some, unique and immutable attribute of the device. You combine it with a measurement of the first kind of bootstrap code that runs on that device, and that produces what's referred to as the compound device identifier. And then, there's that then can be kind of layered in, for more complex systems where you can kind of build up through multiple layers of kind of software and firmware through kind of, hypervisors or container infrastructure or whatever, until you get, to whatever you need to kind of to prove out the underlying layer which supports the application that you want to run. And the second body of standards that I want to refer to is from the DMTF. This is the standards body that defines the kind of protocols and communication, usually for manageability and for kind of supervisory roles within a server architecture. And they've developed a suite of standards called the Secure Protocol and Data Model. And, I've shown an extract on the right-hand side here of a kind of an exchange that would be associated with SPDM. And the way this works is, it defines what's referred to as a requester and a responder. That requester has a, trusted public key that, that it knows is associated with the device it should be talking to. It issues a challenge, at some point in time that, and that can be at kind of periodic intervals, or it can be during the boot cycle or whatever. The responder has the private key, and only the responder has the private key, so that the requester knows that if it gets a signed response that has been signed by the responder's private key, it knows that that part is genuine. And then it can go on and it can request measurements associated with different elements that are running, within the context of the device. And this process can be tied back to the DICE standard if we, tie the key and the key generation to the layer identity. So there's by associating the keys with the compound device identifier, we can combine, the identity of the device from a, TCG or a DICE perspective with the SPDM exchange for kind of transferring the identity to a defined requester. And again, similar to what we saw in the DICE standard, this can be layered. So that we can kind of build up a layer, different layers of attestation, starting from what's referred to as a unique device secret, which identifies the component itself. That unique device secret needs to have certain attributes. The first one is that, it must not be predictable. It has to be a random number. It has to be, constant for each part. So, it only really changes, not during the production lifetime of the part, but really only if you're kind of decommissioning the part or something like that. And it has to be unique per part. We want to individually attest each individual device within the system or within the platform or within the the data center or whatever. So it has to be unique for each and every part. And by kind of layering this, the key derivation on top of each other for each layer, we can build up a system such that the set of keys that are produced by each layer, will only change if the software that's associated with that layer changes, or if kind of one of the foundational underlying layers change underneath it. And then, as the manufacturers or the vendors, kind of during manufacturing, can export the public keys and can, make those available to the customers, such that then during the lifetime of the part, the customers can use a trusted certificate chain to identify, what the public key should look like for a particular part. And then use that, to identify both that part and the to validate the measurements of the software or the firmware that's running at any particular layer within that part. So then, as you can see, there's like this is quite a robust system. It's been shown to work quite well, but it does rely on the implementation of asymmetric cryptography in a number of places. So it's absolutely critical to the security of this, and the reliability of this system that asymmetric cryptography is implemented correctly. And the way that we, that vendors can demonstrate that is implemented correctly is by certifying the implementation of the cryptography. And again, there's a number of different standards that are available in order to do that. And there's kind of a variety of standards associated with the implementation of various different cryptographic algorithms. These are typically specified by the IEC, the ISO, NIST in the US, and various other folks as well. But one of the most kind of prevalent mechanisms for certifying the implementation is using what's referred to as the FIPS 140-3 standard. This is a US standard, but it's widely used across the industry. And its purpose is to promote the use of validated cryptographic modules. So it allows you to have an accredited laboratory analyze your implementation of the cryptographic module and define whether it meets all of the defined kind of standards and whether it is implemented in a robust and a reliable manner. And so there's a number of different standards that are specific to asymmetric keys. And the requirements on asymmetric keys, interestingly, are somewhat different to those of symmetric keys. So, there's the symmetric keys that we would have for protocols or for algorithms like AES that would be used in, say, IPsec or TLS. These are the requirements there are slightly different from the generation of the asymmetric keys. And one of the key requirements from a standards perspective for asymmetric keys is that they have to come from a random bit generator. And then, we kind of burrow down into the next layer of requirements, which are the requirements for the random bit generators. There's one of the major requirements there is that, obviously it has to be random. The values that the random bit generator produces cannot be predictable in any way, and therefore we cannot reuse the same seed over and over. But this kind of creates an issue from an attestation perspective, because what this means is that the asymmetric keys can only be derived once. So from an attestation perspective, that's a gap, or that's an issue for us, because from an attestation perspective, the keys have to be bound to the device, and the keys must persist across power cycles, and they have to be bound to the dynamic inputs, i.e. the measurements of the firmware that's being loaded dynamically onto that platform. And very often there's, persistent storage isn't an option, although, there's within the standards, it is allowed to kind of to store the keys and reuse them, but it's not allowed to derive them a second time. But, there's the derivation of the storage of the keys presents, two problems. One is that, secure persistent storage just may not be available on the device. But the other one is that then, that means that the keys won't necessarily change if the firmware that's being loaded changes. So you can see here on the diagram on the bottom kind of right-hand side of the slide that, the standard requirement is that the DRBG kind of directly feeds into the key derivation process. And that is, based directly on some kind of source of entropy, and that those seeds are unpredictable. So how, what are we going to do? How do we address this? How do we develop the standards in a way that allows us to, persist the same keys across, multiple power cycles, so that we can develop that set of keys which are going to live with the device kind of from production all the way, and when the certificate generation time all the way through to, the decommissioning, through all the repeated attestation that needs to happen throughout that life cycle. So the proposal that we have is to use what's referred to as a key derivation function, or a KDF. And that would use a key derivation key, which, could be constant, and, there's, potentially, stored in the device, or kind of, generated in some kind of a deterministic fashion each time the device powers up. Combine that with the dynamic measurements that are, associated with the firmware, and that, that there's some kind of a derivation method allowed for taking the output of that key derivation function and producing an asymmetric key pair. And so this is what it's that derivation method is is what we really need to be able to certify, and to be able to have a certifiable way of doing that derivation. So what would be required from a standards perspective in order to do that? And the answer is not a lot, really. There's, because, as I mentioned, there's, the requirements on symmetric keys are slightly different. So we can kind of leverage a lot of the definitions and the requirements that are associated with symmetric keys, such that we can, produce something which, for all computational purposes, kind of looks and feels like a random number, but, in terms of the repeatability of it, that it's kind of consistent across boot cycles or across power cycles of a particular device. And then, obviously, we would need to update the requirements to say that this kind of derivation method would be allowed, and that the testing laboratories will be allowed to certify implementations which utilize this method. So, what does that look like in terms of kind of a practical implementation? So, so there's, if we take our key derivation key on the left-hand side, we feed that through a key derivation function. And, I've shown here the example of elliptic curve cryptography. We can then take that output and do all of the curve checking and validity checks that are associated with ECC keys. If you need to iterate through, then you increment the counter, change the label, and kind of repeat that as specified in the standards. Again, there's kind of well-defined methods for doing that. But essentially, you can create an ECC key pair which is consistent and repeatable, throughout the lifetime of the part. And then again, we can do this repeatedly as we work through the different layers in the system. So, we start off with our unique device secret, again, which uniquely identifies the silicon. Combine that with the bootstrap code or the measurements of the bootstrap code. Feed that in as context. That gives us our kind of layer 0 compound device identifier. We treat that compound device identifier as the key derivation key, and then we push that through the KDF with the associated checks to produce a valid key pair. And again, at manufacturing time, the public key can be exported, certified through a certificate chain, and provided to the consumers so that they can have a reliable, trustworthy public key that they can use to query the device via an SPDM exchange. So that's kind of our proposal. That's what we've kind of been working with a variety of kind of stakeholders in the ecosystem to work through. And in terms of where that work is at currently, well, first of all, I suppose one of the things that emerged as we were kind of working through this is that there's, back in 2017, there was an exception granted or an exemption for trusted platform modules or TPMs. And that allowed, TPMs to generate deterministic asymmetric key pairs, subject to review and, based on a particular, but it was isolated to that particular use case and compliance with the TPM standards. What happened in July of this year is that the CMVP or within NIST have decided to extend that exemption so that there's particular implementations can be reviewed and scrutinized by the cryptographic technology group, and they will certify implementations on a case-by-case basis for applications such as attestation. So I guess, the next step for us now is to carry that forward and, partnering with all of you guys in the ecosystem and, across the different industrial segments, is to ensure that that gets kind of written into the standards so that we've got a kind of a more deterministic and a more standardized mechanism for ensuring that we can, with confidence, generate implementations that are both secure and robust and provide that kind of confidence in the provenance of the supply chain. So I guess with that, we'll pause and I'll hand over to Jakob. There's, if there's any questions that have come in, and as I say, please, feel free to post your questions and we'll try and make this as interactive as possible.
Yeah, we have 30 seconds delay between our conversation and our stream. Okay. But I have one question for you. As a person who has nothing to do with hardware, but is there a really such big problem with attacking at the hardware level? Are there many this type of attacks in real world?
So I suppose there's two elements to that. So, I mean, there have been a number of stories in the news about attacks on hardware. There was one in particular that kind of raised a lot of concerns, around, kind of decoupling capacitors on a particular board. But there's, I suppose there's probably the other element, though, is to do with the kind of the bootstrap firmware that runs on the base layer of the device. So there's, it's really important to make sure that the underlying firmware that's running on the device is a authorized, both an authorized firmware component itself and also an authorized version of that firmware. So, for example, if there's security vulnerabilities discovered in a particular firmware release, or if there's kind of multiple valid firmwares for a particular device, but they're not all appropriate for a particular use case, then the vendor can ensure that they only allow that the specific versions that are useful for their use cases to be deployed on their systems. So it's, to a certain extent, it's kind of trying to get ahead of the problem. But it's also a question of, but it's also kind of setting that base layer where you trust the hardware, and then based on the trust in the hardware, you can work your way through all the different software levels, which, to a certain extent can be more vulnerable as you kind of build up to to ensure that your whole top to bottom stack is proven and attested.
Okay, perfect. Thank you very much for your session. We have no question for our audience, but guys, be remember that you should leave your comment or review of this session. Christopher, thank you very much for this session, and I wonder see you in real world.
Hopefully we'll get to. Hopefully we might get over to see you in person for next year's event.
Yeah, perfect. Thank you very much. Have a nice day. See you soon.
Thank you very much indeed. Take care.